Good morning, good afternoon, good evening, whatever the case may be. We are back and better than ever. And today, with the great rock and roll band The Who in the background, we are going to talk about sets and groups, which we have already been discussing. We're going to do a bit more. Let's get to it, shall we? All right, so wanted to talk a little bit today about the associative and distributive properties with unions and intersections. And I know you are familiar with associative and distributive properties. For example, the associative addition, we know that if I have 2 plus 3 plus 4, like this, that is equivalent to 2 plus 3 plus 4. Same sort of idea here, but we're just going to show it using Venn diagrams. So here, I've done the first two here, and we're just going to demonstrate it using the Venn diagram. A union B, so let's do that. A union B is all of this right here. I should have used a different color, sorry. Okay. Union C, so then I'm going to color in all of C. So everything, since it's a union, it's everything that's colored in. And I did A union B first, and then I did union C. So all of this is, this left side here, is equal to A union B union C. So now I'm going to do B union C first. Boom, 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 boom. Oh, little stray there. Let's see if I can get rid of it without ruining it. Yeah, giddy up. Okay, and then let's see. And then I put in the A. The end result is the same. All of the same things are colored. So we've shown that one. What about A intersect B intersect C? So let's do A intersect B first. Okay, so I'm going to do that here, right? And then I have to intersect that where it intersects C. Well, that is just going to be this place right in here. So I'll color that in. So that's that intersection right there, the green area. And now we'll do A intersect B intersect C. So first we have to do B intersect C, and that is all of this, B intersect C, right? And then we'll do the intersection of A, and that's this part, and I'll color all that in. And again, we get the same final area that we are referring to. And then we'll do the next two on the next page. A union B intersect C. So let's do B intersect C, okay, first. It's in parentheses. And then we're going to do the union with A. So I'm going to do all of A here. Let me do that in green. Okay. So all of A, right? So this is a union, so it's all of this stuff. All of this stuff. Everything is included in the union. So that's this part. And then A union B. So let's do A union B. So that's going to be all of this. Giddy up, all A union B, okay, and intersect A union C. So now I'm going to do A union C, so that's this circle and this circle, and then we'll have to be careful as to where they cross here, right, okay. So where does that intersect? Where does A union B, where is it crisscross intersect A union C? And you can see, I'll do it in pink, you see the crisscross here? It's the exact same area that we ended up shading up here. Okay, so that shows that one. And then this one, A intersect B union C. So Let's do B union C, these two circles. So boom, 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 B union C, everything in B and everything in C. It's all these guys. And where does that intersect A? Well, let me do that in blue. Well, here's A right here, right? And where does it intersect? It's just this little football here, football looking thing. So it's going to be that part. So let's see if that's what we end up with the second part. So A intersect B, so that's this guy right here, in the union with A intersect C. So A intersect C, let's see, that's going to be this one right here. So, I forgot. A is also in here. So for this part, A intersect B union C. So here's B union C, all of this. And so where intersect A, that's also includes this part. Sorry about this. And so you can see that we end up with the same parts shaded. Okay. So that leads us to De Morgan's laws, two very important laws in set algebra, which it says the complement of A union B is equivalent to the intersection of the complement of A and the complement of B. So let's take a look at that. So the complement of A union B. Well, A union B is everything in here. So here, let's just do A union B, right, with the pink. Okay. And so the complement, which is what we are interested in, oops, I wanted to do green, is going to be everything outside of A and B. So we want to end up shading down below, hopefully, if De Morgan's law is true, which it is everything outside of A and B. So let's do the intersection of not A naught and B naught, or the complement of A and the complement of B. So the complement of A is everything outside of A. Look at him go, boys and girls. He's cruising through. Boom, 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 boom. Oops, I forgot to include that, right? Because this is outside of B, or outside of A, I should say. Sorry about that. So I did that vertical green. Now I'll go horizontal pink to do the complement of B. So that's everything outside of B, right? So it's this, 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 and this. And where is it crisscrossed? Well, it's crisscrossed all outside the circles. So I'm doing a messy job shading that. But you can see this pink matches the green out here. So we have shown that. Haven't proven it, but we've shown it. And then also the complement of A intersect B. So let's do is equivalent to the complement, the union of the complement of A and B. So first, A intersect B is this, right? So the complement is everything else, everything else. So I'll just quickly do everything outside that intersection there. So it's everything that's shaded outside this intersection. That's what that is. So now let's do the complement of A. Complement of A, everything outside of A. La 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 la. And then boom, 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 boom. And then the complement of B, I'll do horizontally in pink. So here we go, here we go, here we go, here we go, here we go. Wait. Yeah, I'm doing it right. Okay. So the union, so that is, if you look, the union, it's everything that is shaded, everything, everything, everything. And the only thing that's not shaded is in here, which is the same as what we have above there. So if you need to take a second and convince yourself, you can pause and go back and take a look. All right, finishing up. We talked about this briefly. The difference between two sets A and B, sometimes called the relative complement, is defined to be the set of X such that X is element of A and it's not in B. So the difference, the set difference of A and B is also equal to A, the intersection of A and the complement of B. The Venn diagram looks like this. So let's do a couple of examples. Okay, so AI, okay, the set difference of A and B is equal to, let's see, what I'm doing is I'm taking everything in A, then subtracting out anything in B. So 1, 2, and 3 doesn't appear, so there's nothing to take out, 1, 2, and 3, and so that ends up equaling A. II, the set difference of BA, is going to be equal to everything in here, and if any of these appear in A, I have to take them out, but they don't, so it happens to be 4, 5, which is equivalent to set B. All right, so let's do BI, the set difference AB, is equal to ABCD, BDEF. So is there anything in here? If there's anything in here that's in here, I got to take it out. So there's a B minus a B, so it goes away. And then a D minus a D, it goes away. So what's left in A is what the set difference is. So that is equal to AC. And then II, the set difference of B and A. So let me erase this. We're just working it backwards. I think it should be obvious. So BDEF, is there anything in here that's in here? Okay, so again, we're going to take out our B's, right? And then is there anything else? Our D, right? And what are we left with set B? That's E and F. And this is a nice demonstration that this operation is not commutative. Set difference is not a commutative operation. So in general, the set difference AB is not equal to the set difference BA. And you can see that here. AB is AC and BA is EF for the same values or same sets A and B. And finally, let's do this one. The set difference AB is equal to, another way is you can do it, I have a 1 here. Do I have it here? No, it stays. 2, gone. 3, not there, it stays. 4, gone. And then 5 is here, it's not there, it stays. And then the set difference BA, that is equal to 2, gone, 4, gone. So it's actually equal to the empty set. All right, one more concept and I'll be quiet. I usually don't like to go on this long. The symmetric difference is defined by A delta B, and that is equal to the union of the set differences, AB and BA. And it ends up being just those parts of the two sets that they don't have in common, the elements that they do not have in common. And this Venn diagram shows it nicely. So let's just do a couple of examples. So for A, the symmetric difference is going to be equal to everything they do not have in common, which is everything. It is 1. I apologize for my set, that little symbol there. I'm terrible at it. 2, 3, 4, and 5. right? So, I mean, that Venn diagram, let's just do it real quick, would look like this, wouldn't it? A, B would be 1, 2, 3, and then 4 and 5. They're not in common, so they're all part of the symmetric difference. Symmetric difference of A and B here is equal to, let's see, they have B in common, they have D in common, so it's everything that's left, so that would be A, C, E, and F. And then finally, what do they have in common? The symmetric difference of A and B is equal to, they have 2 and 4 in common. So what they don't have in common is 1, 3, and 5. All right. Also note that the symmetric difference is commutative, and it is associative. The symmetric difference of A and the empty set is A because it's what they don't have in common. And the symmetric difference of A and A, they have everything in common, so that becomes the empty set. And the symmetric difference of A and everything that is not in A is the universal set, because the complement of A has nothing in common with the set A. All right, really hope you enjoyed that. We'll go ahead and finish this off with the great rock band, The Who, Baba O'Reilly, and we will see you next time. I am out!